Today we've got Josh Bongard from University of Vermont, who recently gave the plenary at the Invitational Symposium of Trusted Autonomous Systems
Sounds about
down
right.
in Adelaide a couple of weeks ago. So he's joining us fresh from the beach before he disappears back to the US tomorrow. So with that, carry on.
That's it. Thanks very much for the invitation, David. Thanks for taking an hour out to listen to me drone on about robotics. As David mentioned, I was here a couple weeks ago for the ISTES conference on trusted and autonomous machines. I would apologize for taking you away from the nice weather, but I guess that's par for the course for all of you. I prepared this talk for ISTES, and so some of the beginning material sort of for a general audience, not roboticists, so I'll sort of go quickly through that material and get to the good stuff. If you have any questions, stop me. If you have questions about the American election, please hold those until the end. Thank you. Okay. So I wanted to start with this person. This is Nicholas Tinbergen, who won the Nobel Prize in the 1970s for his work on adaptive behavior. And I started my talk at ISTES with Tinbergen because I thought it was an interesting way to approach trusted and autonomous machines. Tinbergen is famous for a lot of very important contributions to the study of animal behavior and adaptive behavior. The contribution I wanted to focus on today is Tinbergen distinguished between two different kinds of explanation of adaptive behavior, which are proximate explanations and ultimate explanations. Basically speaking, proximate explanations are what was the answer that Mother Nature came up with to solve a given problem, and an ultimate explanation of a behavior is what was the problem that Mother Nature was trying to solve in the first place. So why does that matter for roboticists? Well, if you think about a given animal or human behavior that we might want to instantiate in a machine, we can think about proximate explanations and try and build a machine based on that, or think about ultimate explanations and try and build a machine based on that. So if we take, for example, a specific behavior like flight, heavier than air flight, a proximate explanation of how birds fly is they flap their wings. And that was the inspiration in the early days of aviation. Most of the early attempts to build heavier than air flying machines had flapping wings, and as we all know, that didn't really go very far until very, very recently. So if we go back to the original behavior that we might be inspired by, we can offer up an ultimate explanation of this behavior, which is that birds are able to fly because they generate sufficient lift to counteract gravity and drag. The moment you think about that explanation of flight, it leads you as an engineer in different directions, and as we all know how the story ends, the realization that forget about proximate explanations, forget about flapping wings, focus on lift, and you can achieve heavier than air flight if you have fixed wings and your vehicle is traveling sufficiently fast to generate sufficient lift to counteract drag and gravity. So if we now fast forward over 100 years and now think not about trying to build flying machines, but to build autonomous machines, I would argue that in robotics, in many ways, we're still focusing too much on proximate explanations of, in this case now, human behavior. And in many ways, that's holding up, I think, some of our progress in robotics. So I'm going to pick on some of the entrants in the DARPA Robotics Grand Challenge. Some of you might have already seen the blooper reel. So again, a lot of advances were made in robotics thanks to DARPA's Robotics Grand Challenge. But I think it does point up the fact that if we focus on trying to build humans in metal, we can get into trouble. Not quite humanoid, but there you go. This is my favorite one here. We're all roboticists, right? We've all had this experience. It's okay. It's all right. Okay. So as I mentioned, I'm picking on the DARPA entrance here. in my group, what we try and do is not so much focus on the products of evolution. Rather than doing bio-inspired robotics, we tend to try and focus on the process of evolution. So I work in a very, very small subfield of robotics called evolutionary robotics, where we try and take a step back from any specific solution that Mother Nature has come up with and focus on the engine that she used to produce her solutions in the first place, which of course is Darwinian evolution. So this is a screenshot from an evolutionary robotics experiment by one of my graduate students, Francesco Carucci. You create in this case, a first-order approximation hydrodynamic 3D simulation. You create a population of robots that have different body plans and also have different control architectures. You supply a fitness function, and the computer measures the fitness of each of the robots in the population, which in this case is just efficient movement through water. The computer deletes the ones that have low fitness, and the computer makes randomly modified copies of the ones that survive. Right? Pretty straightforward. I showed this video at ISTIS because some people were interested in building very small flapping flying machines. It's also a nice video because it shows that often this artificial evolutionary approach comes up with solutions that look familiar from nature, and also comes up with solutions that aren't that familiar. Right? We're not trying to build any particular fish or any particular species, but basically allow evolution to find the right solution for the ecological niche of these machines. Okay, so that's evolutionary robotics, but as I mentioned, this was a talk prepared for ISTIS, and the focus was on trusted autonomy. So I want to now walk you through some experiments we've done where we apply this evolutionary approach to trying to realize trusted and autonomous machines. So again, going back to Tinbergen, let's pick a particular human behavior in this case, which is collaboration, and try and focus on an ultimate explanation of it. We're not going to focus on the brain circuits of how humans actually collaborate, but what is it that they do? Basically, they trust each other to act autonomously. If we want to have a group of robots or robots working in cooperation with humans, how is this team going to collaborate? The machine members of the team are going to have to be able to be trusted to act autonomously as part of the group. And how can we realize that goal? Well, let's start again with the inspiration here, people. Let's assume we have a team, which might be a military unit. We might have a human soldier that's out in the field. She realizes there's a mountain range in front of her. So there's the perception part. She's looking to see what's in front of her. She may perceive that there are 3 possible paths over the mountain, pass A, B, and C. She then needs to solve the action selection problem. What are the possible actions I could carry out to get over pass A, B, and C? She then needs to have a model of self, right? She needs to know how much water she has, how much endurance, which of these paths might she actually be able to physically summit. She might rule out pass C and realize she only has enough water and stamina for path A and B over the mountains. Finally, in order to function well as part of a team, she also has to have a model of other, which in this case might be her commanding officer. So she's at some level running a mental simulation. If I go over pass A, when my commanding officer hears of that summiting of the pass, will she approve, or would she have preferred that I had gone over pass B? Right? In order to be a good member of a team, you have to be thinking about running mental simulations of the other members of your team. So what I'm going to argue for the rest of this talk here is if we want to build robots that are going to operate as a member of a team, they're going to have these 4 components in some form. If they're missing any of these components, they're either not autonomous or not to be trusted. Okay, so let's start with perception. David and I agreed to disagree at ISTIS over this. I argued that perception is basically a solved problem. It's not a solved problem. It's solved for some perceptual tasks. You all know about the deep belief network revolution, right? Perception is a solved problem. Maybe not solved, but we're pretty good at perception. We're getting better all the time. As roboticists, again, I don't have to convince you of this, you know that action is difficult, right? So at ISTIS, I was telling the audience about branching factors. So why was checkers the first game to fall? Because there's only 8 possible moves. About 10 years later, chess was solved because there's on average 38 possible moves, and as we all know, there was a lot of brouhaha about Go falling to machines just this year. So 20 years after Go, why did it take 20 more years for machines to figure out how to play Go? Big reason is a much larger branching factor. As roboticists, though, we should scoff at these branching factors, right? If you think about humans, again, depending on how you count, we have about 700 muscle groups. We cannot compress or relax all the muscle groups independently, so 2 to the 700 possible moves is an upper bound, but it's still an enormously large number, right? So if you have a robot with enough mechanical degrees of freedom, it's already difficult to enumerate all the possible moves that you can make. Another difficult challenge in robotics, of course, is this issue of modeling of self. So the first project that I want to talk about is some work actually by my colleagues in France. This was a robotics project published in Nature last year, where they incorporated a model of self into an autonomous robot to recover from damage. You can see that the hexapod is missing part of its leg. What if there's no contingency plan for this situation? How can this robot recover from this unanticipated mechanical fault as quickly as possible? In this project, they do so using a model of self. So let me walk you through this project. Here's the physical robot's self model. So before the physical robot is deployed into the field, it has this self model. It's just, as you can see, a virtual hexapod running in a physics engine. They try out a very large number of closed loop controllers on the self model, and they record fast forward locomotion. That's what they're interested in. For each one of these controllers, they also measure some feature of the resulting behavior. So for every controller, they also have a description of the resulting behavior. And so the first thing that they use the self model to do is to take samples from this very high dimensional search space. So this is the space of all possible controllers that could be run on this particular machine. And they sample this down to a subset of controllers which they embed in this, what they call low dimensional, what do they call this here? The behavior space. So in this cartoon example here, this behavior space is 2-dimensional. In the actual project, it was 6-dimensional, but obviously easier to explain this in 2 dimensions. The two axes of this behavior dimension are parameters that describe something of the resulting behavior. So in this case, these 2 features were the fraction of time that the front left leg spent on the ground and the fraction of time that the front right foot spent on the ground. So some feature of the behavior that resulted from that controller. So the 6-dimensional space was the fraction of time that each of the 6 legs spent on the ground. So each pixel in this space corresponds to one controller, and the color of that pixel represents the performance. So in this case, it's fast-forward locomotion. So warm-colored pixels correspond to controllers that produced forward locomotion, and cool-colored pixels correspond to controllers that produce little or no forward locomotion. This behavior space is a metric space, meaning that any 2 pixels that are next to one another produced very, very similar behaviors. So the 6 legs spent about the same amount of time on the ground, and 2 pixels that are far from each other in this metric space produced very different behaviors. So far, so good? Okay. You'll notice that associated with this behavioral space is also a confidence space. So for every pixel in the behavioral space, it also has a corresponding pixel in the confidence space. And the color of the pixels in the confidence space represent the prior probability of how well that behavior will transfer from the self model or the virtual robot to the physical robot. So this is actually a Bayesian approach to this problem. In the confidence space here, we have all cool pixels, the blue pixels, which means it's uniformly uncertain about how any of these controllers will transfer from the virtual robot to the physical robot. Okay, so the physical robot is now going to try and execute one of these controllers in reality. Which one does it pick? It picks, obviously, the pixel that has the warmest color in this metric space. And
Note that the
at least in
robot
this
moves
experiment,
straight
worked
and at a
pretty
speed
well.
of 0.25 meters per second.
At this point, they then introduce unanticipated situation, which in this case is a broken middle right leg here. And as you would imagine, when they rerun that same controller, the robot doesn't do very well at all. So at this point, the physical robot pauses and updates both the behavior space and the confidence space. So in this cartoon here, let's assume that I tried out this controller on the damaged robot, didn't do very well. So it goes back to the behavior space and recolors the pixel, indicating that that controller does not work very well for the physical robot anymore. It also cools neighboring pixels with a Gaussian fall-off. So there's an implicit assumption here that if this controller did not work on the physical robot, neighboring controllers that produce similar behavior are also similarly not going to transfer well to the physical robot.
How do you define the strength of your Gaussian?
I think they fixed it. I'm not sure how they actually determined it, but I think it was just fixed for this experiment. They also then obviously updated the confidence level as well. So the physical robot is very confident that this controller is not going to work well in reality and uses the same Gaussian fall-off to update the prior probabilities. Which controller does the physical robot perform next? It just uses a Bayesian approach where it multiplies each prior probability, each pixel, by what you can think of as the conditional probability in the behavior space, and finds the highest of all of those multiplications, which in this cartoon here happened to be this pixel here. This controller also did not work well on the damaged robot, so it cooled the pixels in this region and updated the confidence here, moved to the next controller, and so on. So use this Bayesian approach to keep updating the behavior space and the confidence space. And at least in this experiment for this particular damage, in about 26 seconds or after 5 or 6 evaluations, it found a controller that successfully transferred from the virtual to the physical robot. Kind of feel sorry for this little guy, right? But pretty impressive. So recovering damage pretty quickly after 4, 5, or 6 trials in about 25 seconds using this Bayesian approach. Okay, so a very nice approach. I mentioned this is by some of my colleagues. Very attractive because it's very rapid. The main drawback of this approach, however, is that there is an underlying assumption that there does exist somewhere in this behavior space a controller that was generated and worked well for the intact virtual robot and will also end up working well for the damaged physical robot. And obviously, as we scale up to more complex robots, it's not clear that that assumption is going to hold up. So what happens if we don't have a contingency plan? What happens if we don't have a controller a priori that's going to work given whatever damage or unexpected situation the robot comes in contact with? So in some actually earlier work, we investigated this where we assumed that the robot does not have a contingency plan for whatever's going to happen to it. So I'm going to walk you through this experiment with a series of videos here. The basic idea here is we're actually going to run 2 search processes in parallel. One which is continuously using the robot's self-model to test out controllers before trying them out on the physical robot. But of course, if the physical robot becomes damaged, the physical robot is no longer going to match its self-model. So we're going to use a second search process, which is also going to adapt the self-model on the fly as we go. Okay, so to show you how this works, we have our robot here. It starts by performing a random action. In this case, our robot just had 2 vestibular sensors, so how much tilt left and right, how much tilt forward and back. The robot has no self-model to begin with, so it starts running this first search method, which is searching the space of self-models. And it's actuating each of these self-models with the same controller it ran on the physical robot, and is recording the virtual sensor data generated by the self-model. And the search process is looking for a self-model that minimizes the difference between the virtual sensor data and the physical sensor data. If you look carefully here, you'll notice that by the end of this short video, the main body is always tilting to the left, and the physical robot actually tilted backwards. So I apologize, my camera work wasn't very good here. The virtual camera was actually rotated 90 degrees. These virtual robots are also tilting about the same angle back. So each of these self-models towards the end here are matching the sensor data from the physical robot, but there are many different mechanical explanations that are able to match the physical sensor data. So the robot knows it doesn't have enough sensor data to proceed. So it goes back to the physical robot and performs a different action, and then continues this search process and is now actuating each of the self-models here with each of the two controllers that it ran on the physical robot, and is trying to minimize the difference between those two sets of virtual and physical sensor data. It goes back and forth between the self-model and the physical machine until it rapidly converges on only one self-model that's able to explain all of the sensor motor data that it's got from the physical robot. Make sense? Okay, so in this particular run, this was the self-model that it came up with. You'll notice it's not a perfect self-model. A lot of the legs are bent here, but it's good enough to explain all of the actions that the physical robot has carried out so far. So now the robot runs the second search process, which is just optimizing controllers on the self-model. The task here is locomotion from the left side of the table to the right side of the table. Came up with this particular closed-loop controller in this case. And tries it out in reality. In this case, it's not a very familiar quadrupedal gait, but it seems to get the job done. Okay, so at this point we now have an autonomous machine which can generate its own gaits, and it can also generate a good enough self-model. It's not perfect, but good enough to explain most of the sensor motor experiences the robot has gained so far. So as good roboticists, we now switch into our sadist mode and torture our machine here by pulling off the bottom part of the robot's right leg. Has no local sensors to detect the fact that the leg is mechanically separated. Actually, the robot can still send commands to the motor, which is dragging along behind. The robot has no camera, it can't see the damage. The only thing this robot knows is from time to time it carries out these exploratory actions that it's tried before, and now it notices that there is something that's different. So it pauses its mission, so to speak, and goes back to updating its self-model. So it unpauses the first search process again and is now trying to explain all of the sensor motor data. It actually can't do a very good job because it's explaining a bunch of data from the undamaged space and one piece of data from the damaged space. So it won't be able to find convergence in this case. So it'll go back and try another action in its damaged space, and eventually it will converge on a good description of self. You'll notice that the robot plays around with the idea that its leg has shrunk a little bit, which doesn't make physical sense. So it doesn't take much more sensor motor data from the physical robot to rule out that hypothesis. And it eventually converges on this self-model down here, where it now realizes it's made up of 3.5 legs. It unpauses the second search method, which is just trying to optimize movement from the left side of the table to the right side of the table. And in this case, it comes up with a qualitatively different gait. You'll notice the motors are also unrealistically strong in the simulator, but turns out good enough in this case. So now the second search process is a different gait, which produces a different controller, which produces a qualitatively different gait, and tries that out in reality, and is able to recover some functionality despite this truly unanticipated situation. So this is work that was funded by NASA, and as you probably know, one of the things that keeps NASA engineers awake at night is what happens if something truly unanticipated happens for which there is no contingency plan. Only then would NASA consider ceding some autonomy to their rover as what they call a method of last resort. Any questions about that? Okay, so self-modeling has a place in robotics, but it turns out it's not sufficient to realize trusted and autonomous machines because it's lacking a model of other. It has a model of self, which it can use for various purposes. What about model of other? Here's an example of a robot that is autonomous but not quite trustworthy. This robot was tasked with optimizing this utility function: turn the handle, open the door, and go through the door. It successfully maximized this utility function, no problem. Right? From the robot's point of view, there is absolutely nothing wrong here. It has maximized the utility function. What's the problem, right? We're all laughing. The robot doesn't know we're laughing. It didn't know that the investigators were obviously shaking their heads and getting ready to write interim reports to their funding agency about this situation. I use this video to try and point that out, right? If you don't have a model of other, if the robot doesn't know that you're laughing or that you're very upset by the course of action the robot has chosen, you may have an autonomous machine, but you have a very, very unsafe machine on your hands. This is important. Obviously, in the civilian space, there's a lot of thought now about how to actually make autonomous machines safe, and if we can't, we should outlaw them altogether. There's an annual meeting now at the United Nations around lethal autonomous weapons systems, better known as killer robots. Right? This is a really important question as roboticists. If we're going to try and create increasingly autonomous machines, how can we also ensure that they're safe, and how can we formally define what we mean by safe? Okay, so again, as I mentioned, one way that we can achieve trustworthiness, or that way we learn to trust other humans, is we assume that they have a good mental model of us if we are a member of their team. So this is something we've been working on, and this is very new work, so please take this with a grain of salt, but this is an attempt to try and deal with this. This is a very simple robot that you see here. This is just virtual robots at the moment, but these relatively simple robots are able to form a model of other. And in this case, the other for these robots is the crowd. So this is actually a crowdsourcing robotics project. For those of you that are net savvy, you might recognize this interface. This is Twitch. So Twitch is a website that millions of people use to watch other people play video games. I couldn't believe that such a website existed before my grad student showed it to me, but it does indeed exist. Within this Twitch website, there are a series of games called Twitch Plays X, where you have the crowd that are collectively playing the same video game. So in the Twitch Plays X domain, you have your users, which have a chat window on the right, and you can type in what you would like the character in the video game to do next. And every few seconds, it tallies up the majority vote, and that's actually what the game character does next. So we're trying to piggyback on top of that idea. So we advertise this as Twitch Plays Robotics. So how does Twitch Plays Robotics work? We send a live video feed from our physics engine that's running locally to the Twitch website, and we tell the users to think of this robot as a pet. You can collectively decide what you want to try and teach the robot next. And once you decide on what the robot is going to try and learn, you then tell the robot, yes, the robot is obeying the current command, or no, the robot is not obeying the current command. So unbeknownst to the crowd, they're basically doing distributed reinforcement learning. So it's a little difficult to see in the video here, but if you look carefully in the top right panel here, you can see people voting on what they want to try and teach the robot next. And in this case, the most votes are for the command walk forward. And it turns out that actually at the moment the robot is trying to learn walk forward. And down here, we'll see in a moment, hopefully the crowd will vote for whether this robot is currently obeying the command walk forward or it isn't. There's one person voting against, and one other person said yes, the robot is. So I'll show you this now sped up so you can sort of see how this works. So we ran this for a couple days. We collected about 6,000 controllers. We had several thousand users contribute several thousand commands and about 15,000 positive and negative reinforcement signals. So we collected a relatively large data set in a relatively short period of time. And then the question was, of course, could the robot actually learn to ground these symbols or come to an understanding of what these commands actually mean? This is the internet, so of course they said all sorts of things, every possible bad word you can ever imagine. Someone issued the command, prove Fermat's last theorem. Someone else issued the command, be yourself. Someone else issued the command, look at the camera, which was actually a good one. The robot had no way to sense where the virtual camera was in the space. Generally speaking, the crowd tended to converge on very motoric language. Walk forward, stay still, go back, turn left, turn right. And it was very simple motoric language. They didn't say, take a prime number of steps. So it's an interesting experiment because we were actually inspired by a lot of work in developmental psychology that shows that parents tend to actually scaffold or simplify the commands or what they're trying to teach their children based on very careful observation of what the child currently is and is not capable of, right? So looks like the crowd is teaching the robots, but the robots are also teaching the crowd what kinds of commands might be learnable by robots that have this particular mechanical makeup. Okay. In this first experiment, as I mentioned, this is very new work. We just launched this last fall. The robots were actually carrying out random controllers, so there was no online learning. All the learning was done offline using this data set that we collected. Here's a visualization of what some of this data set looks like. Turns out that the most common command that the crowd issued was jump. What you can see in this picture here, basically each dot here corresponds to one of the random controllers we ran on our little worm robot here. The vertical position of the point is the fraction of time that that worm spent on the ground. And the vertical position of the point is the normalized reinforcement signal. So -1 means everyone who saw that controller gave the robot a thumbs down. +1, everyone unanimously gave positive reinforcement, and values near 0 means either nobody gave any reinforcement or there was 1 thumbs up and 1 thumbs down, and so on. So if you squint carefully, you can see that there's an anti-correlation between the amount of time that the robot spent on the ground and positive crowd reinforcement, which means, generally speaking, the crowd was honest. When the robot actually did jump, they gave positive reinforcement, and when the robot didn't, they gave negative reinforcement. If you linearly regress against this data, you get the dotted line here. We actually trained this on some deep networks, which could find better patterns, but even a linearly regressed model is a pretty good predictor for this data set. So back to this issue of modeling of other, you can think of this linearly regressed model or the deep belief network that was trained on this data set as a model of other. If the robot is about to carry out a controller for which it knows it will spend 100% of the time on the ground, then the model will predict that the crowd will actually give more than unanimous negative reinforcement. Not perfect, but it's a pretty good prediction. If the robot considers carrying out this action, for which it spends about 50% of the time on the ground, it actually has much more uncertainty about how the crowd will respond. So again, this is a very simple experiment, but it's nice because you can start to quantify how safe this machine is. You can do a sweep across all novel actions that the robot could perform, and you can find certain behaviors for which the robot is much more confident about whether the crowd, in retrospect, will approve of that action or not. And you can also identify subspaces where the robot is very unsure about how the crowd will react. Okay, so back to trusted autonomous machines. A machine that can might perceive a novel and dangerous situation. It might do some action selection and realize that there's several possible actions that might reduce the danger. However, it might vet those actions through a self-model and realize there's only a small subset of those actions for which it's actually going to be able to carry them out. And then finally, it might further restrict its choice of actions using a model of others. If I carry out this action, will the other members of my team or will the stakeholders in the team approve of that action retroactively? Okay, that's all I got to say today. I published a book together with my former PhD advisor, Rolf Pfeiffer. David was telling me Rod's nephew is involved in the group here. Rod wrote the foreword for our book. A lot of the work I showed you today was funded by the National Science Foundation, thanks to the NSF. We have a grant from the Army Research Office and also from DARPA for part of this work. If you want a list of my publications, just Google Scholar Me, follow me on Twitter. I also have an online course that I run out of Reddit, so if you want to try and create some of these evolutionary robotics simulations, the course has a series of programming assignments that'll take you all the way through so that you can evolve controllers and body plans for robots in simulation. Okay, I think I'll stop there and take any questions. Thank you. Sure.
How do you feel that pain receptors work into your model of self? How should they be integrated?
That would be great if you can put pain receptors or localized sensors everywhere that you think something might go wrong. But of course, the issue is what happens if something goes wrong distal from whatever sensor modality you have. So that's what we were focusing on. Yep.
So at the start, you told us that we should look at designs that try to solve this ultimatum problem.
That focus on ultimate explanations of behavior, right?
But,
yeah.
You seem to have in your robots that you present sort of like a brute force approach to sort of finding the optimal solution. But you're doing that with something that's with a robot that's already been designed or built. Doesn't that kind of, like, wouldn't you want to have some sort of idea or evolution on the design of the robot as well, rather than the attitude or behavior?
Yes, absolutely. That's a good point. So the projects I showed towards the end, we already had built the physical robot, which sort of is this proximate approach, approximate explanation approach to behavior. The simulations that I showed you at the beginning, that's really where we tend to focus our efforts, which is coming up with a mechanical structure that's appropriate for the task at hand. So some of the current work that's going on in my lab is putting these two approaches together. So what is a good mechanical design for whatever the task the robot has to perform, but is also most amenable to self and other modeling? So as I just explained in the last project here, it turns out that the mechanical structure, the morphology of this robot focuses the crowd's attention on very specific, very motoric commands, which makes it easier for the robot to model others. We didn't do it, but I imagine if you had a humanoid robot in there, the crowd would probably not be as constrained in the kinds of commands they taught the robot. So you can actually, we'd like to automate this process where in the Twitch Plays Robotics project, the morphology is also evolving, and the fitness of any given morphology is how well it channels the crowd's reinforcement. Right? There's only so much that this robot can do, and the crowd realizes that very quickly. Once they've taught this simple robot all that they can teach it, then we might allow the morphology to complexify a little bit.
This example here, you gave the measure of time the robot is grounded manually. That's nothing the robot found out itself, that's irrelevant.
Correct. Yeah.
Do you have a way of coming up with these models of others by itself? Because when I think back at the robot opening the door and running through,
right.
If the designer of that experiment forgot to put in, actually open the door properly, and it's a reward for not destroying the door, basically, they probably forgot to put that into the model of others as well.
Could be. So that, again, I don't know. That's an open research question, right? Does this robot have sufficient sensor capabilities to be able to model other? If this robot didn't have tactile sensors and couldn't record the fraction of time that it spent on the ground, it wouldn't be able to form a model of other. So in this work here, a model of other has three components. What's the command, something about sensor data, and the crowd reinforcement. So in the case where we trained the neural network to predict other, we gave tactile information. We didn't give proportion of time on the ground, but obviously a deep belief network was able to learn something like proportion of time on the ground. This robot couldn't ground left and right because it had no vestibular accelerometer, so it didn't know what left and right is. So what sorts of sensor modalities do you need to add to ground how many, what kinds of commands you get back from the crowd? It's an open question.
But at the same time, in relation to my question, couldn't you saturate the robot with sensors, as you could with limbs or whatever else, and then kind of say, well, this wave of sensors is redundant, so we'll just strip them down and modify them?
Absolutely, right? It becomes a feature selection problem in machine learning, and that's actually where we'd like to go, right? How does it actually discover a subset of the appropriate subset of sensor modalities to predict reinforcement for whatever the crowd tries to teach it?
So using these evolutionary methods, typically you don't have any little guarantees.
Yes.
So in your work, do you think about that? Can you prove anything, and do you even care about that?
We can't prove anything. What we do care about is it's good enough. So as I mentioned in the case of the self-modeling project, right, it was enough to be able to transfer controllers from simulation to reality. So for me, the proof comes in here, right? It's can you give proofs about whether the crowd will retroactively approve or disapprove of this approach? So evolutionary methods might produce these controllers, but it's after the fact you can use more gradient descent, machine learning, Bayesian approaches where you might be able to prove within this subspace you have a bound on certainty, right? Give me the subspace of possible controllers for which your uncertainty is above some threshold. That's where the proof comes in, not so much on this controller will produce this kind of behavior. Other questions? Yes.
With this sort of staff-like robot
Yes.
at the beginning and the different learning threads, can you give them an idea of how much computation time you actually needed?
I can
progress
for
those models?
I can for this one. I can't speak for my colleagues' work. So this was back in 2006. So we had the robot communicating with a desktop machine at that time. The robot would basically make an action and then do some computation for about 20 minutes. So this, again, was a project for NASA. NASA said, imagine you have all the time in the world. The rover is sitting on the edge of a crater. We would prefer that it doesn't do something dangerous. So this approach was interesting because it's kind of a counterpoint, right? So you have a very large number of controllers saved up beforehand, and it turns out that with this Bayesian approach, you can find something that works in a few seconds. But what happens if there isn't a controller in this set that allows you to compensate for this particular situation, right? Then you might consider using something that's a little slower and a little more open-ended. So I think in the long run, there's going to be a continuum of these approaches given your estimation of the time window you have to recover from whatever's gone wrong.
Just getting back to this original pod design.
Yes.
The sort of bio-inspired people look at this problem as a whole bunch of independent controllers that basically seem to do what they want, and they seem to get really good results using that sort of technology.
Sure.
and almost no brain power at all.
That's right.
So is there a place for both of these sort of technologies?
Yeah, I mean, here I think this is pretty much controller architecture agnostic. I don't think they did use independent controllers for each of the legs in this project. I could be wrong, but I don't think so. They applied the exact same Bayesian approach to a robot arm in the same paper and got the same results, where you definitely have the opposite situation, right?
Yeah.
What happens at the shoulder is going to impact what happens at the wrist. Yeah, that's a good point. Other questions or comments? Yes?
Again, in relation to this experiment, how were the controllers generated?
How are the controllers generated in this project? So again, this was a variant on an evolutionary approach. So they have in the top left here, they have the space of all possible controllers. Pick one at random, execute it on the self model, record these features of the behavior, and that indicates where to store that controller in the behavior space. Produce a randomly modified copy of that one, execute it on the self model. If it falls in a different empty pixel, great. If it falls at the same pixel, then you now have two controllers. You throw away the one that has lower fitness in this case and store that one. And do that for however much computational power you have. Pretty simple search process. Okay, if there aren't any other questions or comments, thanks for your time and your interest. Cheers.